So today we'll be talking about this key value store, which is built on top of non-volatile memory and manages to provide both high availability and can work in a distributed fashion. So typically, for fast access, all the data is stored in the DRAM, and but DRAM is volatile, and in case of failures, you end up losing everything. NVMMs, on the other hand, are a possible replacement for DRAMs. They are cheap and they are non-volatile. But there are some inherent challenges with NVMM, which will need some tweaking of the way recovery happens, which is what this paper focuses on. So they build out this canned store, consistent, available, non-volatile, distributed key value store, and they leverage NVMMs. And they focus on how recovery happens. So typically, there are two ways to do recovery in this in case of failures. One is where an entire replica of data exists. So there are two servers, both have the same copy of data. One fails, the other one takes its place. But with NVMMs, it's the cost is a challenge. The other way that this happens is in case of a failure, you bring back all of the data from the log to the main memory, and then you have all of the data in the main memory and you start serving client requests. But because of NVMMs have low write throughput and have some and high storage density, that's a challenge in case of NVMMs. It's not fast enough. So these are the So they provide a workaround with this. While building this out, proposing a design for this, they have three assumptions in mind. One is that the real world workloads are skewed. Some keys will be accessed more than other keys, and some keys that are accessed will be very co-located together. The other thing that they say is that in a system, availability means that it needs to respond to a request in a particular time limit, which is the SLO. So as long as you are fulfilling the SLO, a little bit performance degradation is fine. They also modify the Raft protocol to work with the the design decisions that they have taken while building the store out. So in CanStore, this is like they use three kinds of nodes: the primary, the backup, and the witness. Primary, the main storage medium for the primary node is an NVMe hash table. Same for the witness. For the backup, NVMe, the main storage medium is SSD. NVMe is there so that you can get best of both the worlds. You can get the right throughputs of SSD and you can get the latencies of NVMe. Right. So when everything is working fine and nothing is failing, how do GET works? They are pretty straightforward. Client sends a GET request and primary responds with a value. In case of puts, now puts for puts, a write quorum need to be created. When the primary gets a put request from the client, it replicates it to a backup, and only when the backup has committed and responded to the primary with a success, only then does the primary respond to the client as a success. Along with sending the put request to the backup, the key and value, it sends that key and value pair to the witness as well. Witness also writes that particular value and reverts back to the primary, but witness is not a part of the write quorum in case of while fielding client put requests. So all of these three nodes, they write different parts of data in different ways. So primary commits the key and value to the NVMe hash table. Witness commits the key and the logical timestamp of the update to its own storage. Backup, it first writes to the NVMe buffer, then after a while, it writes to the SSD for long-term storage and eventually updates the DRAM index. This is how they use SSD. So whenever recovery needs to happen, the data is read from SSD. So here the advantages of SSD come into play, and while replicating put requests, they use NVMe, so that gives the latencies that NVMe provides, which is why this decision. Backups, they are like very critical. The backup nodes are very critical in recovery, so their performance is very important. These guys, they structure backup in a particular way. So they say that all the backups have multiple workers, and each worker will have their own exclusive write spaces in both the SSD and the NVMe's. There will be also these storage spaces both in the NVMe and the SSD will have spaces for hotkeys and for cold keys, two separate areas. I will come to this reason later. There are 3 threads in each worker. One thread handles the RPCs, other writes from NVMe to SSD, and the third is for garbage collection. So the RPC thread, it fields all the requests coming in from the primary, the put request and other requests for replication. And it in case of put request, it sees the key, it checks if it belongs to the hot space or the cold key space, and writes it to the appropriate NVMe buffer. After the second thread, the one that writes from NVMe to SSD, it continuously keeps an eye at the NVMe buffer. After it collects some entries, it writes them to the SSD for long-term storage, and then it also updates the DRAM index and writes to it the key, the update timestamp, and the page where the key exists on the SSD. The garbage collection thread, the main function of this is to prune the log and to move the keys that are not hot anymore to the cold space, and move some keys from cold to the hot space, whatever is based on whatever the hotkeys are at any point of time. This is where there are a lot of writes to the SSD taking place, and which will be very harmful, which is very harmful to the SSDs in the long run. So this is where they say that there are ways to optimize this. So based on like we keep saying hot and cold keys, like we said in the start that some keys are accessed more than the other keys, and so the keys that are accessed more than the other keys are called hot keys, and the other keys are called cold keys. So how does this identification happens? The primary node does most of this identification because it is the one fielding client requests. After it has collected a bunch of hotkeys, that classification, it sends it to the backup. Backup takes that and segregates all the keys present in the NVMe buffers and even also in the SSDs into hot and cold keys. During steady state operation, there are certain overheads that are apparent, and those are first, there is a lot of protocol related communication that happens along with replication, which they say that the paper states that any protocol related communication such as heartbeats is piggybacked on top of the RPC, the write RPCs, the write calls, for the client put requests whenever possible. The another overhead, communication overhead happens as the propagation of popular key, which happens every second. According to the paper, it's not very significant. A third overhead is when a write needs to take place, and a lot of messages are exchanged for a right to succeed. So these are the overhead that they mentioned that they've taken care of. Right. So how does leader election and log reconciliation happen in case of failures? So two things that are important to note here is that the backup nodes are not a part of the leader election. Only witnesses can take part in the election process, and thus only witnesses can be the new primaries. The catch here is that witnesses are not a part of the right quorum. So witnesses might not be fully aware of the committed updates, which means that they, if elected, a witness might be behind. So that's why they changed the leader election protocol a little bit to solve for this problem. So this is how it works. So when a witness sends a call to other witnesses to requesting votes, it sends that call, and it also sends the log, like what happens in raft. It sends that call. It also sends the last its own last log index. The responses that it receives have a vote, or if not a vote, then the log index coming from the responder. If there is a gap in the log index, for example, if the responder is ahead and the node that requested the vote is behind, then the node that requested the vote, it updates its own last log index and uh, stores the value that it was at in some temporary variable. Once the leader election happens, the newly elected primary, compares those two values, the old log index and the latest log index. And if it sees that there's a gap, it starts a log reconciliation process, which is nothing but sending calls to the backup to send across all the logs that it has missed. So that's what's happening in the second part of this image. A log reconciliation process is happening. The request log request is sent to the backup, and the backup reverts back with the log entry. Once this process stops, when it receives all logs, that is, they've made a statement here saying that if the new primary sends a request for a log that does not exist on a backup, they can just discard that request, because if a log does not exist on the backup, it can be safely assumed that that particular value was not committed. Over here, because they want to speed up recovery, they have made a few changes to how things work. One of those things is those things is a proactive recovery failure. So when the primary actually fails, the recovery phase starts long before the actual failure happens. It's called the proactive recovery phase. In this phase, they detect this by using soft and hard timeouts. As soon as the soft timeout elapses, they see that, okay, there might be a failure that might happen. And as soon as that happens, the witnesses, they send requests to backup to send across all logs, and the backups start sending all logs to the witnesses. Now, as soon as a heartbeat is received, this process is stopped. Else, as the hard timeout also elapses and the system goes into failure. The key thing to note here is that soft and hard timeouts need to be set very carefully, because if the soft timeout is too short, then there's a very high chance of false positives happening. While if similarly for hard timeouts. So after proactive recovery starts, after this, the leader's election starts if the system has gone into failure. After that, the log reconciliation starts, which is something that we discussed earlier. Now, once the primary has received all logs from the backups, it's sufficiently up to date. That's when the live recovery begins. So the new primary does not wait to be fully up to date before starting serving client requests. So as on one hand, it's fielding client requests, and on the other hand, it is still fetching. It is still being brought up to date by the backups. So this is what the live recovery period is. It's live because the system is fielding client requests, and recovery because it is still recovering from failures. So right, in this case, the put requests work in a similar way. A write quorum is used to replicate the request. Gets, on the other hand, are a little bit different. So when a get request comes in, if the primary has the value, it reverts to the client. If not, it asks the backup for that particular key. Backup checks its own its own logs, and it finds the page where that key exists, and it sends across all the keys that are present in the page to the primary, and primary responds to the client with the value. The catch the backup is sending all values present in a page because of the uh, co-locality thing that we talked about at the beginning, that if some keys will always be accessed together, they cite some reference in the paper um, uh, which they say makes for better, which they say make for popular access patterns. Also, it's a way to just update the primary in one go for a bunch of keys. So some of the challenges with the way recovery happens and the way that the system is set up is one of them is there is an SSD bottleneck. So SSDs are, again, there are tail latencies associated with SSDs. So they say that it's best to split the data across, to have multiple backups and to shard the data across multiple SSDs. So this way, all the requests won't be directed to one SSD, and multiple SSDs can bear the load, which means that we'll see a better throughput. The second thing that they say is that now if we shard the SSDs, if we have multiple backups, means we have a large cluster, which means there'll be a communication overhead because there'll be uh, because, for example, when some replication happens, or when recovery happens, multiple nodes will be sending data to multiple other nodes. So that is something that needs to be managed. Third overhead that they mention is that the communication overhead during leader election is twice as great as in a standard primary backup setup. The other failures that they talk about, but not a lot, which we can discuss in the discussion, is backup failure and witness failures. Witness failures, so according to them, witness failures are not very critical because the system can make progress even if the witness fails, but it's better to restore the witness as in case of failure, so that the standard levels of fault tolerance can be maintained. In case of backup, the system must, because backups are involved in write quorums, it is important for that backup that has failed to be excluded from the write quorum, and then once it comes back online, it needs to be caught up properly to be included back in the write quorum. So backup failure is critical for them. So for evaluation, okay, so for the evaluation setup, they are not sharding the cluster. They are using a standard 3-node cluster because of the challenges in NVMe availability. The client and server are running the same number of threads, and the client is sending requests. Each thread on the client is sending requests sequentially. Only this paper talks about two protocols. One is the steady state function, and the other is the recovery protocol. So, but in evaluation phase, they only measure the the performance of the recovery protocol. The system is evaluated on a get heavy workload, and SSD block size is fixed at 32 kb because it is said that it affects throughput. So these are some of the things that they have kept in. They have made. These are some of the decisions that they've made while evaluation, and this is the only part of evaluation that I will cover. I won't go further than this. So I think we can close the presentation here. Thank you all for your time.